this looks like a statement we've already proven, right? But no, notice here that I am asking, I put a plus above the z here. Well, why? Because I'm asking, instead of for all integers a and b, I'm specifically going to be asking for all positive integers a and b, which would include numbers from 0, 2, 3, up until infinity. This does not include 0, and this does not include the negative numbers. Okay, so is it true that for all positive integers a and b, if a divides b and b divides a, then a is equal to b? Well, I think that this is going to be true because we already know that, for example, something like this cannot be both true. Only one of them is true, and that's going to be this one. This one's going to be false. If we take something like 2 and 4, an example I use a lot, and then flip that to 4 and 2, we know that this up here is going to be true, and this down here is going to be false. If you're not sure why, watch the previous videos or simply write these out yourself and show me that 2 is a multiple of 4. You can't possibly do that without making what 2 has to be multiplied by a fraction, which you are not allowed to do by definition of divisibility. So, of course, when you look at this, you always think, okay, well, then it has to be that 1 is 1, 2 is 2, 3 is 3, right? Flip any of these, it's just the same thing, and all of these are, in fact, true by our definition of divisibility, so it's looking like the statement is going to be true. So let's go ahead and try and prove that. Now, this is going to be a little bit tricky because I'm going to end up doing a proof within a proof, but we'll get to that point when we get to it. First, we want to suppose our P statement, or because it's a for all statement, we want to say let. We want to say let a and b be integers such that a divides b and b divides a. Now remember, our goal here is to show that a and b do in fact have to be the same number, but we aren't there yet. Let's first unpack what it means to say a divides b and b divides a. What that means is that then b must be a multiple of a, or b must be a times m, and for b to divide a, it must be that a is a multiple of b, so a must be b multiplied by n, where m and n are integers. Fantastic. Okay. So where can we go from here? Well, I'm thinking that we clearly need to somehow get these two equations to get us to this point. We have to somehow go from these two into here. And the only way to really go from two equations to one is to probably put one equation into the other, substitute something into something to put it all into one equation. So because a and b are in both equations, we can obviously rearrange this. We can plug a here by plugging this a into here, or we can go the other way around and we can plug b into here. So what we're going to do is, let's go ahead and try that, right? Like that's something you're obviously going to go ahead and do when you're first writing a proof like this. So let's try that. We can say, therefore, a is equal to bn, which is going to equal to am times n. Okay, fantastic. We can then say, then a is equal to, or we'll say so. We'll say, so a is equal to a times mn. Now, what can we do here? We can definitely divide both sides by a, right? So we can then say, or we can just say it as a sentence, then divide both sides by a, and then we can put an arrow, or maybe we can't put an arrow. I'm not gonna worry about the arrow notation. I'm going to put a comma and just say 1 is equal to m times n. And then what do we find? Well, then it must be that, we'll say next. It must be that 1 over m is equal to n. Okay. How can we get this? Because maybe we can plug... Hi, so this is future me here right now. I've cut myself off because while watching me prove this, I noticed I'm a bit of an idiot. I should have noticed that when I said 1 is equal to m times n, I should have noticed the only way the product of two integers can equal 1 is if the two integers are either 1 times 1 or -1 times -1. Those are the only two possibilities for this to be true. Everything I'm about to do after this is very much overthinking the problem. I should have just seen this off the start. And then on top of this, I should have noticed that, hey, because b is equal to am and a is equal to bn, or whatever I wrote, whether it's m or n, if I mix those around, it doesn't really matter. I should have noticed that because b is positive and a is positive, the only way to multiply a positive number by an integer, to multiply a positive times some m and get a positive number, is for n to be positive, and the exact same logic will apply here on the right hand side, which means the only possibility is for this to be 1 times 1 is equal to 1, which means m is equal to 1, n is equal to 1. So if m is equal to 1 and n is equal to 1, then of course m is equal to n. So everything you're about to watch is me completely overthinking the problem, but I think it's useful for you to see a different way of approaching this, and b, to show you that math proofs are hard. Like, I had to do this on the spot. This was very hard, and I'm sure you were yelling at the screen saying, this is something I should have seen. It can only be these two, and it has to be this one, because for this to be positive, it must be that this has to be positive. Okay, so what I'm thinking is, in order to get to here, we probably want to get to it to be something like AK is equal to is equal to bk, and then we want to show that you can factor out this k and you can say a is equal to b, right? Or in our case, you want to show that maybe they're both m or they're both n, because that's the only way I can think of making this true. But to do this, you're going to have to argue that m and n are going to be equal to each other, right? And how can we argue that m and n must be equal to each other so then we can use this? Well, I'm thinking because we have a fraction here, we encounter a problem. Fractions are oftentimes a scary thing to be dealing with when you're dealing with integers. Because when you're dealing with integers, fractions introduce the possibility of something being a decimal place. So the only way for 1 over anything to be an integer is if whatever the denominator is, it's less than 1. K must be less than 1. Oh, okay, that's the thing. Okay, I got it. So when we say this, in order for n to stay an integer, m cannot be greater than 1. This cannot be true, right? Because when we say m is greater than 1, then this would end up being something like 1 over 2, 1 over 3, so on and so forth, right? You can think of any integer in the world that's positive and greater than 1. So then we break the rule that m is greater than 1 and n is an integer, but n can't be an integer if n is equal to a fraction like this. So, okay, we know it can't be true that m is greater than 1. So m, in this case, must be less than or equal to 1. And what do we find? Oh, I need to suppose that a and b are positive integers. Okay, because remember we're supposing what's up here. So we know this must be true for n to stay an integer and for m to stay an integer. Now we know m cannot be, of course, a fraction, right? M cannot be 0.5. M cannot be 0.1 because these are not integers. So this means m cannot be 0 because you can't divide something by 0. So this means m must be less than 0. This can't be n because then n is no longer an integer. Okay, so this is what we've found so far. So far we have found that if we have a number line, right, like this, and we have 0 here, we have 1, 2, 3, dot, 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 dot. And then on the other side, we have -1, -2, -3, dot, dot, dot. We find that if this must be true, because our algebra obviously shows that that must be true, it must be that m can be equal to 1, m can be here, and then we find m is equal to 1, n is equal to 1. Can't be here because then m is equal to 2, but n is equal to 1/2, which is not an integer. In fact, we find that for all numbers here, n ends up not being an integer. So we can summarize this as that's an integer, but this stops being an integer. Okay. Similarly, okay, so we know that this can't be true, so it could be 1. Let's look at numbers less than 1. We know that m cannot be up here for the same reason as down here. Okay, I'm gonna black these out, so I'm going to just say that's not possible for either number. Okay. We then have to notice that obviously if m is here, then n ends up being here. So yeah, we notice if m is somewhere here, n ends up being between 0 and 1, so n ends up not being an integer, which is kind of what we argued here. So we know that can't be here. Okay. Can still be 1 though. And then we find neither one of them can be 0 because it's impossible to get 1 over something equals 0, I think, unless I'm missing something, unless m is astronomically large, but we're not dealing with limits here. So we say they can't be 0 either, because if m is 0, you have 1 over 0, and you can't divide by 0, so then n can't be an integer. Okay. And if n is 0, then what on earth is m going to be? Infinity? Infinity is not an integer, unfortunately. And then we run into the same issue here, where if m or n are large numbers like this, or large negative numbers, we find the other one has to be a decimal. But we do find, as we found earlier, that if m is equal to -1, then we find that n also has to equal to -1. So we found the only two cases where this equation works and m and n stay integers. Okay, fantastic. So we know m and n have to be 1 or -1. Which one is it going to be, though? Do we have to break this up into cases? No, I don't think we do. We don't need to break this up into cases because a and b have to be positive integers. That's really, really important here. In order for these to stay positive, we know this is a positive number and this is a positive number. We know this is a positive number and that is a positive number. Well, what does that mean m and n have to be? Well, we know if it was something like positive times negative, you're going to get a negative. If it was negative times negative, it's going to be positive, and a positive times a positive is going to be positive. Well, in this case, we already know one of these positives is already going to be fixed, right? We know there's going to be a positive in this product, which means the only way to get the product, the A here or B here, to stay positive is going to say that m must be positive and n must be positive, right? So we're looking at this case down here. Okay, fantastic, which means that m and n must be equal to 1, which means m has to equal to n. Okay, we got there eventually, fantastic. So this is kind of the reasoning that I decided to go through here. So we can then say for m and n to remain integers simultaneously, I probably spelled that close to being correct, m cannot be more than 1 because then n, or here, let's do case by case, right? Case 1, m, if I say if m is greater than 1, then n is not an integer. Case 2, if m is 0, then n still cannot be an integer, since 1 over 0 is undefined. Fantastic. Case 3 is going to be if m is less than 0. We find that if m is less than -1, then n is not an integer because n becomes just a negative fraction. So it just mirrors case 1. Okay. Then we want to say, let's take the n cases, right? Case 4, n is greater than 1, then m cannot be an integer. Case 5, n is equal to 0, then m cannot be an integer. There's no integer where you're going to have 1 over something is equal to 0. Okay, and then if we say case 6, n is less than 1. Okay, if n is less than 1, well, we just get the same thing as case 4. Then it can't be that m is an integer because m would have to be less than 1 for n to stay less than 1 or greater than 1. Fantastic. So the only option we're left with, since neither of them can be 0, neither of them can be more than 1, neither of them can be less than 1, the only thing left is case 7, m is equal to 1, so then n is equal to 1, and if n is equal to 1, then m is equal to 1, so m is equal to n. Okay. Or let me rewrite this. The only remaining possible values for m and n in order for them to remain as integers is m is equal to -1 or m is equal to 1, where or actually, you know what we can say here? We can use an if and only if. So we can say where m is, is this even on camera? Let me quickly check that before I even write this down. Where we can say where m is equal to -1 if and only if n is equal to -1, and m is equal to 1 if and only if n is equal to 1. Full stop. Then we're going to come up here. We're going to continue our proof. We're going to say where m cannot be -1 and n cannot be -1 because then a is equal to b, n is not, because then a is not positive as we supposed in a equals bn, right? Since b is positive. Okay, fantastic. And we can say, and or no, that's it. We can just say, there we go. So they can't be, we've gotten rid of all the cases leaving -1 and 1, and we know that it can't be -1 because then what we supposed for A to be positive is not true. So we could say, so M and N can only both equal 1, and if M equals 1 and N equals 1, then M is equal to N. Fantastic. Okay, we're almost there. We can then say, thus, A is equal to Bn is equal to B times M. Fantastic. And where can we go from there? We can say B is equal to AM. So what we can then say is we can plug in our B, I'm thinking, right? Let me think. Oh, I know what we can do. We can rearrange both of these equations for M, right? We can say M is equal to A over B, and M is equal to B over A. So A over B is equal to B over A, which we can then simply multiply both sides by B, multiply both sides by A. We get A squared is equal to B squared, and then we can square root both sides and we get A is equal to B. There we go. So we have proven that for all positive integers A and B, if A divides B and B divides A, it must be that these M and N have to be integers. We know that by definition of divisibility. And they must be positive in order to stay consistent with our assumption here, which means that the only options are M can't be greater than 1, M can't be 0, and M can't be less than -1. Similarly for N, which leaves our M and N to only be equal to -1 and 1. We know they can't be negative because then it breaks our first assumption. So that leaves that they can only be equal to 1. And if they're both equal to 1, we can say M is in fact equal to N. And then when we plug that into our equations, we can make both of these rearranged for M or for N, whichever you choose. And then we can make them equate to each other, showing that A squared is equal to B squared. And then there's no reason we cannot square root both sides. And when we do that, we in fact get to the conclusion that A is equal to B for when A and B are exclusively positive integers. Fantastic. Okay, so we can just say, so in conclusion, when A, B are positive integers and A divides B and B divides C, it must be that A is equal to B. Okay, this was a very long and complex proof. I hope my reasoning made sense. I know it was very long, but that's just the process of proving, is you sit here and you think of how on earth can I explain this. So I decided to break it down into cases. You probably don't have to. You can probably just skip from here immediately to probably M is equal to N if you find a way to write this in a neat sentence. But there we go. We've now proven that this statement is in fact true.